This is the final part in our series of talks having a look at the compilation process within C++. In this one, we're going to briefly have a look at some of the techniques that the compiler will use to try to optimize our code. As a reminder, the reason we're doing this is that if we understand how the compiler tries to optimize our code, and the things that it can do and the things that it can't do, it means then that we can write our code in a manner that will, in as far as it's possible, best help the optimizer. The general context here, we're talking about optimization, it falls under efficiency. We can define efficiency in terms of minimizing the use of some resource. There's generally, when you're talking about code, there's two things that you could optimize. One is the execution time. So you reduce the amount of cycles machine instructions need to be executed. Or the second one is that you can minimize the amount of memory that needs to be used for running the program. So you can either optimize it one way or the other. Generally, you can't optimize it for both. And there's a trade-off here that if you optimize it for speed, quite often that means then it has a slightly bigger memory footprint. You need to use memory to speed it up, and some optimizations will do that. If you try to optimize it to have as small as memory footprint as you possibly can, then generally it runs a bit slower. Again, for some of the techniques for saving space are a bit more resource intensive in terms of machine instructions. So bits of swings and roundabouts in terms of what is most important. You might think, okay, optimization, if we're, say, running, it's a C++, it's a compiled program. I've said in an earlier talk, we can take as long as we want to compile the code. So why not produce optimally optimized code? Something that is as fast as it possibly can be. Problem with this is that it's almost certainly not possible. Optimization is an NP-complete problem, which means that it's almost certainly the case that for large sizes you can't feasibly, at least based on current models of computation, exhaustively explore that particular space. What that means then is that basically all compilers we have nowadays, they use heuristics, rules of thumb. They sort of, well, I'm going to test for this, or if I see this, I'm going to do that. So sort of sensible rules of thumb or case-based algorithms that, in this particular case, here's what I should do to speed it up. Now, what this means then is that if we have compilers, and that's what we do nowadays, that use heuristics, that use certain cases, we need to make sure that we write our code in a way that the optimizer will be encountering structures that map onto the heuristics that it uses, that is, that sees it in a way that it can make sense of. Because if we don't, then it's not going to be able to apply the optimizations that it has available to it. And there's the risk here that, we could go from having something being optimized to going to have something not being optimized at all because the compiler is not in a position to introduce any form of optimization on it. The key to understanding how the compiler goes about doing this is it really works in flow analysis. So what the optimizer is going to do is going to have a look at a chunk of code and to ask, okay, well, what changes does this block of code put in? And from doing that, it can work out, okay, if I run this here and the only thing it changes is that, is there a more efficient way of doing that than whatever it is we went through to get to it? So effectively here, it has to understand the changes that our program puts in. And if it can't understand the changes, if it can't track the changes that we're doing because we've maybe written it poorly, it means that it just can't put any optimization at all. It's going to give up. It's going to say, well, I can't understand that, so I'm just going to go with whatever was there. In terms of doing this flow analysis, the optimizer will break the program up into what's known as basic blocks. So a basic block is a sequence of instructions that there's no branching, there's no jumping. You go down to the top, you go down to the bottom, one entry point, one exit point, that's it. And those basic blocks are what the optimizer will look at by way of tracking and understanding what has actually happened. So I've got a few examples of them over here. So you look at the code on the right hand side. So lines 1 to 4, it doesn't really matter what we're doing here. We're setting up a few variables, we're calling a method, we're doing a calculation in line 4, but it is a block. Line 1 goes on to line 2, goes on to line 3, goes on to line 4, and it's a top in, bottom down. Line 5, this is where the block has to end, because here there is a potential change in the flow of control. It's an if statement. And depending upon the evaluated condition, we will do one thing or we will do another thing. Now you can see within the if, we've got a couple of lines of code, and that is a block in its own self. We always come in and then we exit out. Within the else, again, we have another 4 lines which are executed with no branching or other stuff within that. And again, that provides us with a block of code. And then finally, 17 and 18, after the if-else, we have our final block of code. So we can chop up our program into these number of small blocks of code, where each block of code is a single entry point, a single exit point. Now, within a block of code, it's actually quite easy for the optimizer to track what is happening. To look, for example, at a div or quote as the 2 variables we have, and to work out, well, what changes are made to those particular values. So, for example, it might be able to work out from line 2 to line 4 that we have a redundant calculation at line 2, that div assigned a value of 2 and doesn't change within that particular block. So it knows after block 1, div's always going to have a value of 2, and things along those particular lines. The problem with the if statement, or the if-else statement, is that whenever you return from that if-else, you may have variables which could have 1 of 2 different values depending upon how the if condition was evaluated. Now, tracking 2 different values, again, that's not too difficult. If you have a more complex structure with multiple nested ifs and elses, you go from having maybe 3 to 4 to 5 to 6 potential values for a particular variable. That's where it becomes more difficult, and that's where compilers will put in an upper limit that they may be able to track up to 4 different variants of a particular variable. But if you write code that goes into a 5th, then it's just going to give up. It's going to go, nope, I can't do it. It's beyond my ability to track it. So at that point, we lose any optimizations that it was going to put in because it's not able to understand the code that we have written. So as a general rule of thumb, and one that actually would serve you well, if the code that you write, if you avoid unnecessarily complex branching, so sometimes it may be necessary and there's nothing you can do about it, that's just unfortunate. But if you can write it in a way where there is more simple branching structure to it, it means then that we are maximizing the probability that the compiler, the optimizer, will be able to apply as optimizations to the code that we have written. Here's an example of some of the things that the optimizer is able to do. So things like constant folding. So compute and use the value of a constant expression or sub-expressions at compile time instead of actually doing it at runtime. So for example, if I had I'd written a piece of code, say 2π, so I was doing some calculations involving circles or whatever, and I wrote 2 times math.py. Now, it is a constant value. 2π is always going to have a value of 2π. It's never going to change. So the compiler could work out that particular value at compile time and then store that particular value, so it's never ever worked out at runtime. Constant propagation then, so if a variable is assigned a constant value, doesn't change, then replace that variable with the constant value. So in this case here, if let's say I have a constant, maximum number of, I don't know, people is equal to 10, depending on the program. So I have a variable, and I've assigned it a value that never changes, will always have a value of in this case, say 10. Now, important thing to realize, if you have a value, it is actually slower to use a value than it is to use just a literal value. Because given a variable, we've got to go to the variable, look it up. So that's accessing a location in memory, take the value out of that location in memory, and then use it. So it's quicker simply to say that if you know what that value is going to be, just insert the value directly and to save that memory lookup. Sub-expression elimination. So this is an example of one where you actually use a bit more memory, but you do it in a way to save some machine cycles. So we've got a sub-expression that's used several different times in the same block of code. If we want, and we've worked out that the block doesn't change, then we could calculate it and store it at the start or whenever is appropriate, and then reuse it as need be. So you can see here in lines 1 and 2 over the left-hand side, A is equal to B times C plus X, and D is equal to B times C plus Y. So B times C is a constant expression. And an example given on the right, we calculate that, store it, and then make use of that calculation in lines 2 and 3. A few other things we have here. So dead code elimination, we've seen sort of an example of that in the previous lecture, where if we've worked out that some of the instructions are unnecessary or don't change things or have no meaningful impact or can never be reached, then we can just simply trim them out. Loop invariance, so if we have something within a loop that never changes, so we're doing the same calculation over and over again, we can bring that out of the loop at the start, do it there, store it, and then reuse it. Induction, so it comes into the dependencies we have between some variables within the loops, and there's some optimizations we could apply there by basically merging dependent values together. This is I suppose, a more interesting one, known as strength reduction, and it gets into the compiler having an understanding of, for different types of machine instructions, how quickly they get to be executed. So a good optimizing compiler will be able to look at the code. If it sees a sequence of expensive computations, maybe you'll then to work out a different sequence of less expensive computations that will give us the same answer. So an example we have here is a for loop where we're storing some values within an array, and it's just 2 times I as we go down through that. Good optimizing compiler will be able to work out that 2 times I, well, that's basically the same as adding on 2 every single time we go through that. So effectively, in the example we have underneath, we've got a variable temp, so again, a slight increase in memory usage, and we are assigning that value to the array and then increasing the stored value by 2, which is functionally the equivalent. But it transforms it into a sequence of multiplications and assignments into a sequence of additions and assignments, which, depending on hardware, generally will execute a bit more quickly. So that was some examples. Most compilers, if you simply say, here's my program, off you go and compile it, they'll just do it with little in the way of optimization. So we quite often need to turn it on. We need to tell the compiler the type of optimization that we are looking for. Do you want to minimize the amount of memory or to the amount of machine instructions that are needed in terms of what area to work on? Debuggers, generally, they not particularly compatible with optimization because they insert their own code, and they want to be able to have sufficient breakpoints where you can then sort of go through and step through the code that we've written. So generally, when you're developing it, you run in debug mode, optimizations are turned off, you turn into release mode, and you apply whatever optimizations is appropriate for your target platform. So summary then, to best exploit or the compiler, to get it helping us as best as possible, we want to write our code in a way that the optimizer is going to be able to make sense of. And general rule of thumb here is that keep it simple. Don't do unnecessary branching. The more branching you put in, the more difficulty the optimizer is going to have. and keep it nice and simple. That means then the optimizer will be able to apply, hopefully, the full range of optimizations it has available to it.